Hello and welcome to a discussion on liquids and beyond. So, as we just got finished with the discussion on intermolecular forces and we see them exhibited in the condensed states of liquids and solids. Um, Liquids exhibit certain traits that are related to IMFs, especially, and this is you see this hand touching water. We take for granted so much about the properties of water, one of which the surface tension. Um, Water has some pretty unique properties, and part of it, water's character allows it to be swallowed easily. There's all kinds of things about it you never really think about. Um, Liquids with a large surface tension resist um, increase in surface area, which, if you drop it in water droplet out of a pipette, you'll see it drop down and it'll take on a spherical shape, and that's because the exertion of the surface water molecules grabbing onto water molecules at the surface can't grab onto anything above, so they tend to grab and it forms this shape. Um, Polar molecules have a lot more surface tension than nonpolar molecules have. One of the things we see a lot in chemistry is capillary action. It's a spontaneous rising of a polar liquid in a narrow tube. Now there's cohesive forces and adhesive forces at work there. The cohesive forces are intermolecular forces among the liquid molecules for each other, and then the adhesive forces are forces between the liquids and their container. So we do this in a polar container such as glass, but it's possible for us to exhibit the opposite. Instead of seeing a concave meniscus like we see when the glass is polar, we might see in glass, if it were a mercury, which is um, uh, uh, not going to be attracted to glass, we'll see a convex surface. So when we see a convex meniscus, that means the cohesion is greater than the adhesion. When we see a concave meniscus, that means that the adhesion is overcoming the surface tension. So um, that brings us to viscosity, which is resistance to fluid flow. Liquids with large IMFs tend to be very viscous, and this is things like sugar. And sugar is a large molecule with lots of OH bonds, which leads to lots and lots of and this is liquid sugar, which would be something like, or aqueous sugar, something like molasses or syrup. But glycerol is a great example, something you can buy at the store of a molecule that's very, very polar, and so lots of hydrogen bonds can be formed, so it's very thick. Um, and this is a measurement of the different standard weights of oils, and these oils are all different, and it has to do with their chemical makeup that gives them their more increasingly viscous properties. So more complex molecules are more viscous because they tangle up, having more and more and more molecules interacting with each other. Now, this comparison, gasoline versus grease, has everything to do with the length of the hydrocarbons. So the longer your hydrocarbons, the more viscous your substance is. Grease and tars have carbon chains up into the 30s, 40s, 50s. So we're going to talk about structures and crystal lattices only at face value, but I'll show you some slides if you're curious, because it is rather interesting how solids pack. But we do need to differentiate amorphous from crystalline. So first of all, amorphous solids. Disordered, usually long chain molecules, plastics, asphalts, rubber, and even glass to a degree exhibit amorphous solids. When you cool silica really rapidly, you get glass. If you cool it slowly, you get large crystals and it forms quartz. Anyway, crystalline solids are highly regular arrangements, important word, of components, and they exist in a 3D lattice, um, which is a repeating pattern of system points designated by the centers of the components. It could be atoms at each of the points, it could be molecules, it could be ions. All the solids exhibit their own 3D crystalline shape at the fundamental unit. The unit cell is the smallest repeating unit of a lattice. You don't need to learn anything regarding that. It's interesting, but it's not part of the AP exam. Coordination number, again, you don't have to know this, but it's the number of nearest neighbors surrounding a particle in a crystal. It's essentially counting how many other points, objects are touching that particular particle, or not touching, but adjacent to. So these are some crystal lattice patterns. I'm going to go through these kind of rapidly when you see these. So you don't need to know them. You do need to know that we use X-ray diffraction with crystals to help determine what they're made of. And this is where Robert Moseley determined the atomic number of the things on the periodic table in the early 1900s was through X-ray diffraction. But anyway, I'm going to talk about allotropes, and then we'll jump into the crystals. There's a term we'll use called allotropes. Allotropes are different makeups of the same substance. For example, carbon has several allotropes, diamond being one, charcoal being another, graphite, fullerene, graphene. Those are all allotropes of carbon. They're made of the same thing, but different structural makeup. Sulfur and phosphorus each have two different allotropes. So you'll hear that term. I don't want it to be too foreign to you. It applies to any substance that's made of the same stuff, but it's got a different makeup, got a different construct. So these are the crystal slides. I'm just going to go through these, relatively rapidly. If you would like to pause and take a look at them, please do. But these are just for, at this point in our learning, FYI. Okay, so we need to focus on a couple of types of crystalline solids. Properties of a solid depend on the nature of the forces that hold it together. That's really important. We understand that. First, we have ionic solids, obviously made of ions. Ions are at the lattice point. Strong ionic forces hold all the particles together. They're very stable. They have a very high melting point, and electrostatic forces obviously hold them together. Smaller ions fit into the holes between larger ions, and so you see sort of a pattern of big, small, big, small, big, small, typically when you see an ionic compound's crystal structure. And again, just like all other physical structures, the attractions are maximized and repulsions are minimized. Then we have molecular solids, where molecules like water or carbon dioxide or allotropes of certain elements are at each lattice point. Molecules, well, these allotropes are the actual molecular solid, where those atoms are at lattice points. Molecules are lattice points held together by LDFs, dipole-dipole, or hydrogen bonds. It just depends on what it's made of. Okay, so if it's a nonpolar molecule, then that nonpolar molecule will be at the lattice points, and it'll probably be rather cold if it's a solid. Strong covalent bonds within the molecules hold the molecules together, but relatively weak IMFs between the molecules hold the solid together. The atoms within the molecule are closer to each other than to atoms in adjacent molecules, and this indicates that they have pretty strong bonds between the atoms. Carbon dioxide, sulfur allotrope, iodine, and phosphor allotrope have no dipole-dipole forces. The last three are solids at room temperature because the LDFs are stronger in larger molecules that have more electrons. Okay, and now we talk about metallic solids, where we have metal atoms at the lattice point. And a pure metal, obviously, would be made of only that one atom. But you can also use this type of bonding and talk about, or this type of solid structure for alloys. So we describe the bonding in a metal substance as non-directional covalent bonding, where electrons are dissociated from the atoms in particular and are just part of the entire metal sample. So those spherical atoms are packed together and bonded equally. What you see in the diagram is sort of a side view of what would be a cross-section of an atom or a series of atoms of magnesium in a solid sample. And these gaps you see are electron position patterns, and up top we have a valence shell molecular orbital, which means electrons that have been disengaged from their atoms, and they're able to just kind of move about the sample of the metal. You also have a molecular orbital that's empty above that, And that empty molecular orbital is where excited electrons from metal are able to communicate and transmit electrical current or heat. Another type of crystalline solid is atomic solids, where atoms are at the lattice points. And obviously, if it's going to be atoms, they're going to be relatively nonpolar. They'd have to be nonmetals, because otherwise it's a metal, right? Um, but like argon, being a noble gas, is not terribly attractive as a bonding partner for anything. So a sample of argon can be frozen into clear ice, like you see in this image. This is argon sublimating at room temperature. So the covalent network solid, to give you a little more detail, typically we see diamond and silicon compounds. They're essentially one giant molecule. Whatever the base unit is, that's a nice ratio, but the covalent network solid is a giant molecule of covalently bonded atoms. There's very little IMFs to concern yourself with when you see this, especially with like diamond. Graphite does have IMFs that hold together graphite sheets. That's why when you imagine that you have a pencil, okay, this is the tip of the pencil. When you're writing, you're shearing off graphite sheets, and that's what lands on your page. These weak bonds are what you're overcoming. The graphite sheet itself is the covalent network solid. Okay, and here's the page you've all been waiting for. Once upon a time, one of you came up and said, I just want a list of all the covalent network solids so I can just see them, so I know them, because I'm afraid that I'm going to get a question where I have to identify it. And my answer is always, you're not just going to get listed a name and be asked if it's a CNS, but you do need to have a good idea. So what you should notice about all of these is they have a couple of things in common. Boron, carbon, silicon, carbon, silicon, boron, silicon and carbon, silicon, germanium, and then the weirdo aluminum nitride. I don't have a good answer for why aluminum nitride exhibits this behavior, but it does. It's in our list, so we go with it. Now, I would expect if you're given a question about the properties of a substance and whether or not it's a covalent network solid, you're going to get data or information that leads you to that conclusion. You're not expected to memorize anything. So, know that. Or you're not expected to memorize a list. So again, I wanted to talk about this general trends and strength of attraction. There's a big gap here on purpose. There should be a big gap there. London dispersion forces are by far the weakest of the attractive forces when taken alone. If you have enough London dispersion forces in a large molecule, you can coalesce a nonpolar substance into a heavy, hard tar. But the trick of the matter is it's held together by weak forces. Dipole-dipole forces are a little bit stronger than LDFs. Dipole forces are present in covalent compounds that are polar. Covalent compounds that are polar, in which nitrogen, oxygen, and fluorine are responsible for that polarity, exhibit hydrogen bonding. Again, a weak force. And then our big gap, our strong force. Metallic bonding, ionic bonding, plain old covalent bonding. Covalent network solids are increasingly stronger and stronger. Now the covalent bonding is going to be very, very wide gap of how strong the bond can be, but it exists somewhere between ionic bonding and metallic bonding. You're not going to be asked to list. You're going to be given information that leads you to conclude what makes a stronger bond. Having an understanding of what these substances do when they bond, though, gives you a lot of pre-understanding of what to expect when you're questioned. I hope this video helps you better understand the different types of bonding still, and we'll see you on the next one.